Welcome to qnawire.
So we have a geothermal power plant. It is a single flash with state numbers um, given in the problem. Okay, so we have, let's see here, we have a production well. So we have, again, something hot coming in here from a geothermal heat source. We got a mass flow rate of 230 kilograms per second. So we're coming in here through a flash chamber. Um, and then into a separator where we separate the liquid and the vapor. So the liquid kind of drains off, and then the vapor winds up going into the turbine, which then produces some energy. So we can maybe put that in here so we get some power out here, and then we have some heat transfer out in the condenser. Um, Before we, let's see here, before we basically pump it all back in to the reinjection well. And again, we take the water from there from the separator and then pump it back in with again, mix it with the stuff coming out of the condenser and pump it back into the reinjection well. Oh, let's see here. Let's see here. Let's see. We have the um, temperature at the of the stuff coming out of the geothermal well, and we're assuming it's a saturated liquid. Now it is, let's see here, it makes 35, yeah. So let's see, at the flash, let's see here, after here we have um, 100 and 500 kilopascals. So let's see here, exits at, let's see here. So then we have the isen, isen, isenthalpic flash process results in vapor is separated from the liquid steam. The steam leaves the turbine at 10 kilopascals. So we're leaving here at 10 kilopascals with a moisture content of 5%. So X4, did I put that down here? Yeah, it's in here. X4 is 95%. And what else did they tell us in here? It is routed to a reinjection well along with the liquid coming off the separator. Okay, yep. So I'm assuming, oh yeah, so this is 230 degrees C. And again, is flashed to a pressure. Okay, not sure exactly how these this uh, um, flash thing works, but anyway, the flash chamber. But anyway, we have what we have here. All right. So um, doing our analysis, then we can get the looking at some things here. We can get the, let's see here. We know that the temperature and the quality at 1 here, so we get the enthalpy and the entropy there. At 2, we know the pressure, and then we know the enthalpy, which is the same as the enthalpy at 1. So we can get the quality factor at 2, and that winds up being about 17% by mass. So again, we have mostly liquid, but then some vapor here. So we needed to get it up to a higher pressure. And then so we can get the entropy at 2 also. And let's see here. Yeah, mostly liquid. Again, by volume though, very different. Mostly liquid by weight, but by volume, it would probably be definitely mostly vapor by volume. So then we know, let's see here, we know m dot 3, the flow rate out of here is the quality. So we're getting the uh, quality is this. So we basically, we're dividing the vapor and the liquid here. So m dot 3 is x2 times m dot 1. Right? So we basically get, a fraction of this flow here as vapor coming out of the separator here. Now, the pressure, we were told again that is going into here, and that's a saturated liquid because this was, kind of in the two-phase region. So we had the saturated vapor and the saturated liquid, which we separated. So the enthalpy and the entropy. At 4, we have a pressure and a quality factor that we're given, so we can get the enthalpy and the entropy. At 5, we have the pressure, because we know it's the same pressure as at 2, which is the same as at 3. And we know we're going to assume that that is now the saturated liquid at that pressure. So we have enthalpy and entropy there. And again, we know that the mass flow in 6 is just from conservation of energy. The mass flow rate through 6 is the mass flow rate at 1, which is the same as at 2, and then minus the mass flow rate at 3. So by mass, again, we're rejecting most of this back into here. We're just getting by mass, not a whole lot of steam. About I don't know. Let's see, that would be it's a small percentage by mass of steam. So we can get the power generated by the turbine, because if it's isentropic and adiabatic, it's the mass flow rate through the turbine times the change in enthalpy, and that winds up being about 10.8 megawatts. So if we have a temperature of the surroundings, and we assume that it's the liquid be a saturated liquid, the water would be a saturated liquid in the surroundings, we can get the surrounding enthalpy and the surrounding entropy. Now we can also get the energy flow in to the system, and that is just the let's see here. That is the mass flow rate at 1 times the what do you want to call it? The change in enthalpy from the surroundings. What it would be this is basically the geothermal heat energy that is putting in, because if we basically took our surrounding water and then heated it up in this geothermal, whatever is going on down here under the ground, this is basically the heat that we would be putting into it. So this is the rate of heat transfer, essentially the rate of heat transfer from the geothermal process down here. So that's about 203 megawatts. So we can see we're not really doing a great job here of extracting the work out. But again, it's basically, it's not an easy process to do, because you don't want this hot water going into your turbine. It might be, there's other stuff you could do. This is not a very efficient way to do this. So, this is not going to be great. But so we can figure out the efficiency, which is very low, which is 5.3%. Again, so we're going to have to, we could do a little better with this, but it's not an easy thing to, kind of take everything, get everything, we could, again, use this hot water for something, possibly, and try to get some energy out of that hot water. Anyway, we wanted the specific exergies at the various states. So again, we have states 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, and 6. I didn't do 5 because it's just, there's nothing there. It's all going back essentially. Now, coming out of here, it's at just surrounding conditions. So again, it's just the enthalpy minus the surrounding enthalpy, what the water would be at the surrounding, and then here. So we basically just need to, whatever I is, So, you know, at 1, we'd put H1 and S1 here, and at 2, at H2 and S2. So again, we calculate, go through and plug those all those numbers in. So the exergy, the specific exergies at those states are just given here. Okay, so again, at this is 1, 2, 3, we have the most, right? Because we have that's what's going into the turbine. At 6, we don't have a lot because again, that's the water. So there's not a lot of exergy in the water. At 1 and at 2, we dropped a little bit here over this flash chamber. And then we basically separated it out, what was coming in at 2 into the steam and into the water. And then at 4, this is what we're getting out of the, or this is 6, this is this, and then or 4 here is what we're getting out of the turbine, what's flowing out of the turbine. So let's see here. We wanted the exergy of the geothermal water at state 6. So here. And so we can take the mass flow rate of the at 6, which we have here, and multiply it by the exergy at state 6, which is here, and we get this. We get about basically about 17.3 megawatts of exergy flowing at state 6. The exergy destruction in the turbine is, again, kind of the exergy change. The exergy change in the turbine times the mass flow rate through the turbine minus the power out of the turbine, and that winds up being about 10.9 megawatts. And how much did we get out of the turbine? Actually, we got, you know, almost exactly the same amount out of the turbine. So it's the fact that these numbers are very close is kind of coincidence, I think. I'm not sure that why that should actually be, but it's very much about the same. We destroyed as much exergy as we got power out, essentially. So the thermodynamic efficiency then is roughly 50% of this. The second law efficiency is roughly 50% for the turbine. And the exergy flow into the plant is M1 dot times the specific exergy at 1, which we have this here, and we have M1 dot here. And that winds up being about 49.8 megawatts. So that's the exergy flow in. The exergy destroyed in the plant is simply the exergy flow in minus the work in the turbine. Now that winds up being about 39.0 megawatts. And so then the second law efficiency of the plant is this divided by this, and that winds up being 21.8%.